Now we are going to study moving charges and magnetism. From our earlier studies we know that when a current is passed through a conductor, a magnetic field will be produced around the conductor. To demonstrate it, here there is an arrangement. In this arrangement, a conductor passes through a cardboard, a horizontal cardboard through which the conductor passes carrying a current I. If we place a small magnet needle on this cardboard when the current passes in this way, the compass needle or magnet needle deflects in a certain direction. The direction is given by the tangent drawn to an imaginary circle. The direction shown by the compass needle will be tangential to an imaginary circle with this conductor at the center of the circle. That means here this will be the direction and here this will be the direction, and this is the imaginary circle. So the direction of the magnetic field formed by the conductor will be circular around the conductor. We can find a number of lines of magnetic field in the form of circles around this conductor, as the conductor carries current in the upward direction. Now the direction of the magnetic field due to the current is also shown by this diagram. Here this circle with a dot at the center shows outward current. It can be outward current or outward magnetic field or outward electric field, etc. This is the notation used for that. Now this circle with the dot at the center shows a current flowing in the upward direction. That means outward from the board or outward from the plane of the paper, like this. If current passes in this direction, then the magnetic field will be like this. The magnetic field will be anti-clockwise if the current is towards us. Similarly, if the direction of the current is reversed, that means if current passes in the downward direction, then the arrows of the magnetic field will be in the opposite direction, in the opposite sense. Here, as we view from the top, this will be anti-clockwise, and if the current is reversed, this will be clockwise, like this. Here, current passes in this direction and the magnetic field due to the current will be in this direction, as shown by the curled fingers, like this. The thumb shows the direction of the current and the fingers, curled fingers around the conductor gives the direction of the magnetic field produced. So this is the way for representing the outward current and the magnetic field, and also the inward current and the magnetic field. Okay. Thus we see that when a current is passed through a conductor, a magnetic field will be produced around it. The direction of the magnetic field, and the direction of the magnetic field is given by the right hand graph rule, Fleming's right hand rule. If the current carrying conductor is held in the right hand such that the thumb gives the direction of the current, then the curled fingers around the conductor gives the direction of the magnetic field. That is a law. That means if a current carrying conductor is imagined to be held with the right hand such that the thumb gives the direction of the current, then the curled fingers gives the direction of the magnetic field around the conductor. Now we know that the current is flow of electric charges. That means we see that moving charges create magnetic field around it. Moving charges create a magnetic field around it. If instead of current we consider the flow of positive charges in the direction same as that of the current, then the magnetic field formed will be like this, the same way. That means the flow of positive charges, protons, alpha particles, etc., if they are the particles moving like this current, then the magnetic field formed will be like this. But if electrons are moving in this way, then the flow of current will be opposite to that. Or in order to create a magnetic field like this, electrons should flow from the top to bottom along this line. So a moving charge produces a magnetic field around it, and the direction of the magnetic field is given by Fleming's right hand rule. We have seen that there is a magnetic field around a moving charge. So if this moving charge moves through a magnetic field, then the two magnetic fields may interact and the charge experiences a force. So a moving charge experiences a force in a magnetic field. In addition to the magnetic field, if there is electric field also, then there will be a net force acting on the charge particle. That means if a charge particle carrying a charge q moves through a space where both electric field and magnetic fields are present, then a resultant force acts on the particle, and the force is given by F vector equals q into E vector at r vector plus q into V vector cross B vector at r vector. Here E vector at r vector and B vector at r vector are the electric and magnetic fields at the point with the position vector r vector. But this may be simply written as q into E vector plus q into V vector cross B vector. This part, the first part gives the electric force. This is the electric force, and the second part gives the magnetic force. Therefore, we get the magnetic force as F vector is equal to q into V vector cross B vector. This is the magnetic Lorentz force. This is total force acting on a particle when it moves through a space where both electric field and magnetic field are present. This net force is called the Lorentz force, and this alone is called the magnetic Lorentz force. Now we consider the magnetic Lorentz force F vector is equal to q into V vector plus B vector. The value of the force clearly depends on the amount of charge q, the velocity V vector, and the magnetic field B vector. Its magnitude may be expressed as F is equal to q into Vb sin theta, and in vector form this can be expanded in the form F vector is equal to qVb sin theta into n cap. Now the direction of the force is given by the direction of the cross product V vector cross B vector. This is shown in this figure. Here, if we consider the rotation from V vector to B vector through the smallest angle, this rotation from B to B through the smallest angle, that means here theta, appears to be anti-clockwise when we observe this plane from the top. So the direction of the cross product will be towards that side. That means the direction of the cross product V cross B will be towards that side of the plane containing V vector and B vector, from which the rotation from V to B appears anti-clockwise. So the direction of the force acting on the charge particle will be in the upward direction. It is also given by right hand rule or right hand screw rule for the cross product of two vectors. That means if we curl the fingers, of the right hand such that the curled fingers gives the direction of rotation from V to B through the smallest angle, then the stretched thumb gives the direction of the force acting on the particle or direction of the cross product to V vector plus B vector. Now, if the charge is negative charge, then the force will be in the opposite direction. That means if it is negative charge and is moving in the same direction, then the force will be in the downward direction. This is clear from this diagram. Here we consider two charges, plus q and minus q, moving in the same direction with velocities v vector, in the same magnetic field b vector. Then the force acting on the positive charge will be towards right, and the force acting on negative charge will be towards left. That means these two forces are acting in the opposite direction, and so the direction of deflection will be in the opposite sense. That means here the negative charge will be deflected in the anti-clockwise direction. That means it will trace a circle like this, but the positive charge traces a circle in the clockwise sense. So, if positive and negative charges move in the same direction in a magnetic field, then the direction of deflection of the two charges will be in opposite sense. Now, coming to this, we can write the expression for the magnitude of the force as F is equal to QVB sin theta. Now, if theta equals 0 or 180 degree, clearly the force acting on the particle F will be equal to 0. Sin 0 equals 0, sin 180 also equals 0. That means if the charged particle moves parallel to the magnetic field or anti-parallel to the magnetic field, the force experienced will be equal to 0. The force experienced by the charged particle will be equal to 0 if it moves parallel to the field or anti-parallel to the field. If theta equals 90 degree, the force experienced will be maximum and is given by F is equal to QVP. Using this relation, we can define unit of magnetic field as follows. If F is equal to 1 Newton when Q equals 1 Coulomb, V equals 1 meter per second and theta equals 90 degree. Then B equals 1 SI unit, it is called 1 Tesla. So unit of magnetic field may be defined as follows. If the force acting on a charged particle, if the force acting on a charged particle of charge 1 Coulomb moving with a velocity of 1 meter per second perpendicular to a magnetic field is 1 Newton. If the force acting on a charged particle of 1 Coulomb moving with a velocity of 1 meter per second perpendicular to a magnetic field is 1 Newton, then that magnetic field is said to be 1 SI unit or 1 Tesla. Now, Tesla may be expressed in terms of other units using the relation. We see that F is equal to QVB when theta equals 90 degree, and therefore B equals F divided by QV. B equals F divided by QV. Therefore, 1 Tesla or unit of magnetic field is equal to Newton divided by Coulomb into meter per second, or meter here and second here. That means 1 Tesla equals a Newton second per Coulomb meter. Okay. Now let us study force on a current carrying conductor placed in a magnetic field. Here CD is a conductor of length small l and area of cross-section capital A, placed in a uniform magnetic field of intensity capital B vector. It is inclined at an angle theta with the direction of the field. This conductor carries a current capital I from C to D. Now, we know that flow of current is flow of charges. Here we consider that this current is due to the flow of charge carriers, each of charge small q, moving from C to D. Now, if a charge q moves from C to D, then with a steady velocity, if a charge small q moves from C to D with a steady velocity called drift velocity, then the force acting on the charge carrier is given by Lorentz magnetic force as a small f vector equals q into small v vector cross capital B vector. This is represented in this figure. Here V is the direction of the velocity, B is the magnetic field, direction of the magnetic field. Then the direction of the force will be perpendicular to both P vector and B vector. This we have already learned. Now we can use this expression for the force acting on each charge carrier moving inside this conductor, and thus we can find the total force acting on the conductor by multiplying the number of charge carriers inside the conductor with the force on each charge carrier. That means the total force acting on this conductor when it is placed in a magnetic field is given by F vector equals N into small f vector, where N is the total number of charge carriers inside the conductor. Now we can calculate capital N as capital N equals the number of charge carriers per unit volume of the conductor may be taken as a small n, then the number of charge carriers per unit volume into total volume of the conductor. That means area of cross-section capital A into length of the conductor. This is the total number of charge carriers inside the conductor. Therefore, the total force acting on the conductor is given by capital F vector equals small n into A into L into small f vector. That means this is equal to n A into L into small q into V vector cross B vector. This is the total force. This is the total force acting on the conductor. Now, this can be written as A into L into N Q V vector cross B vector. This NQV vector can be taken as a current density. So this can be written as this is equal to A into L into NQV vector is the current density J vector. Therefore, J vector cross B vector. Now, this J vector has a magnitude J, and J into capital A gives the current density into area of cross-section gives the current through the conductor. Therefore, this may be written as A into J into this vector sign can be shifted to the top of small l. That means this can be written as L vector cross B vector. Why? L vector has a direction from C to D. When the current flows from C to D, J vector also has the direction from C to D. Therefore, we can shift the vector notation to L vector. So, we can write this as A into J means the current. Current is a scalar quantity, but current density is a vector quantity. But the modulus of current density J into A gives the current which is a scalar quantity. So I into, we can write this as L vector cross B vector. So this is the force acting on a conductor of length L placed at an angle with the direction of a uniform magnetic field B vector. I is the current flowing through the conductor. This is the expression for the force. We have F vector equals I into L vector cross B vector as the expression for the force acting on a conductor. Expression for the force acting on a conductor. Now the modulus of this force is given by F is equal to I LB sin theta, where theta is the angle between the direction of L vector and the B vector. This is the angle. If this angle is 0 or 180 degree, that means if the conductor is placed parallel or anti-parallel to the magnetic field, then value of the force becomes 0, because the sign value becomes 0 for 0 degree and 180 degree. Therefore, we get F is equal to 0. F equals 0 for theta equals 0 or 180 degree. In both the cases, the force acting on the conductor will be 0. That means no force acts on a conductor if it is placed parallel to a magnetic field. Now, the maximum value of this force is clearly given by the maximum value of the sine value. The maximum value of sine of an angle equals 1, and here this occurs when theta equals 90 degree. That means when the conductor is placed perpendicular to the magnetic field. If the conductor is placed perpendicular to the magnetic field, then sine theta becomes 1. And therefore the force takes the maximum value, F max equals ILB. This is the maximum value of the force acting on a conductor when it is placed perpendicular to the direction of the magnetic field. F max equals ILB. Now, if this conductor is not straight and if it is bent, then we can imagine the conductor to be made up of a large number of small strips, each of length dl. Then the resultant force acting on the conductor is expressed as F vector equals sigma of I into dlj cross dlj vector cross b vector. This is the expression. Summation is done for all the small strips. Now, what will be the direction of the force? Force has the expression F vector equals I into L vector cross B vector. So, what is the direction of the force? The direction of the force is given by right hand rule for the cross product of two vectors. That means F vector will be perpendicular to both the L vector and B vector towards that side of the plane from which the rotation from L vector to B vector through the smallest angle appears anti-clockwise. In case L vector right lekana, B vector direction at an angle theta. അതുകൊണ്ട് L vector cross B vector എന്ന് പറയുമ്പോൾ L to B rotation എടുക്കുകയാണെങ്കിൽ through the smallest angle theta എടുക്കുകയാണെങ്കിൽ this rotation appears anti-clockwise when we view from this side. So the direction of the cross product will be towards us. This is the direction. This is also given by right hand rule. That means curl the fingers of the right hand such that the curled fingers represents the rotation from L vector to B vector through the smallest angle. Then the thumb gives the direction of the force acting on the conductor. ആ രീതിയിൽ നമുക്ക് ഡയറക്ഷൻ പറയാൻ പറ്റും. അപ്പോൾ ഇതിന്റെ ഡയറക്ഷൻ കണ്ടുപിടിക്കാനായിട്ട് റൈറ്റ് ഹാൻഡ് റൂൾ യൂസ് ചെയ്യാം, റൈറ്റ് ഹാൻഡ് സ്ക്രൂ റൂൾ യൂസ് ചെയ്യാം ഫോർ ദ ക്രോസ് പ്രൊഡക്റ്റ് ഓഫ് ടു വെക്ടേഴ്സ്. അതുപോലെ തന്നെ നമുക്ക് ഡയറക്ഷൻ കണ്ടുപിടിക്കാനായിട്ട് വേറൊരു റൂൾ കൂടിയും അപ്ലൈ ചെയ്യാൻ പറ്റും. If the conductor is placed perpendicular to the direction of the magnetic field, then the direction of the force acting on the conductor is also given by Fram's left hand rule. Stretch out the forefinger, middle finger and the thumb of the left hand in mutually perpendicular directions. If the forefinger points in the direction of the magnetic field, middle finger in the direction of flow of current, then the thumb gives the direction of the force acting on the conductor.